Hi, today I'm going to demonstrate how to teach a lecture about solving the heat equation using LiveScript proficiently. In a LiveScript, you can describe a problem with some text, implement a solution with the code, and then run to immediately get the output. Text, code, and output all together will create a compelling story, and we learn from stories. If you need a quick review of LiveScript features, please watch the video linked in the transcript. Now let's go deep into our lecture. So what's the problem? It's the heat diffusion along a thin one-dimensional rod. An image can help visualize the problem immediately. Given the initial temperature across the rod at time zero, and holding boundaries at the same fixed temperature, we want to compute how the temperature will change due to the heat conduction across the rod and over time. By getting deeper into the structure of the heat solution, we'll be able to discover that transient state will exponentially decay toward the stationary equilibrium. The time decay will strongly depend on thermal behavior of material. Diffusivity will play a key role. This property describes the attitude of a material to transfer heat without heating up too quickly. All sections can be organized into a summary table, and it will allow to scroll up and down or quickly jump to next section. To provide more background, we recall the key Fourier's findings. Fourier analysis is the awesome idea to represent every function, even with jumps, as a sum of harmonics. We'll see how to compute the Fourier coefficients of the initial temperature of the rod. Note that any equation can be easily added from Insert tab, click on Equation, to open the equation editor, where you can pick many symbols, a sum, a derivative, or an integral. Fourier's law is the proportionality of heat flow rate and temperature gradient, the minus confirming the common experience that heat always flows from hot to cold irreversibly. The heat equation is an amazing concentration of a Fourier's law, thermodynamics, and conservation of energy, where diffusivity pops up as the key parameter, and this is actually the main equation we want to solve together. Finally, we have two important ratios to highlight. First, the relationship between a D and K. Please don't be confused. Conductivity K tells us only about the heat transfer rate, while diffusivity D considers also the temperature change occurred during the heat transfer. So, larger diffusivity requires also a small heat capacity. And the other remarkable ratio is the time decay of the transient. So, when changing the material, remember, the larger the diffusivity, the smaller the time decay. It means that the transient will decay faster. And now let's make an exercise to explore real numerical values of diffusivity. In this page, I found the values for different materials. I put them into a table and saved it into a math file. So now we can load the math file containing this table called Materials. And here is the MATLAB table. And then we can reorganize the data to map the material name directly to its corresponding diffusivity value by using a containers.map constructor. For example, we can take diffusivity for iron just by typing the name. Okay, 23. To help choosing the material name, we can open the table, copy the name column, and then go to Insert tab, Control, and pick a drop-down. We can paste the list of all materials. And now everybody can scroll this list and pick any material without typing the name. We can choose iron, steel, or pyrolytic graphite, so we have a quick way to determine the diffusivity for any material in this list. For future reusage, we'd better save this map into the map file. LiveScript can also help understand the physics behind the heat equation. Conservation of energy is the starting point. Look at units, because they can tell us what energy balance is about. Time change of heat energy is due to incoming heat flux, and this balance is in watt or watt per volume in the differential form. Thermodynamics and Fourier's law allow you to express energy and flux in terms of temperature. By embedding these laws into energy balance, the heat equation follows immediately, and we can see where diffusivity comes from. As an exercise, you can try to derive again the heat equation using the equation editor. In another exercise, you can learn how to use the symbolic variables and then assign units that are visualized in the output too. This way you can verify the unit of diffusivity ratio. And you can also derive partial derivative equations and check if they are consistent. That is, if the two members have the same units. And you can repeat this for all the equations we've done before. Okay, we have completed the first part about the story, some key facts. Now we are ready to start the second part with more code to visualize the transient structure, build the heat solution, and simulate the heat diffusion in different materials. So let's go. To solve the transient problem, we focus on homogeneous boundary conditions, it meaning that boundaries are held constant at 0 Kelvin degrees. We'll freeze this boundary condition to a general heat structure. The solution structure is a series with the space and time well separated, sign and exponential being the eigenvectors of differential operators. Boundary conditions are satisfied due to the value of lambda, and the negative exponential decaying to 0. The greater the diffusivity, the faster the decay. So we are going now to visualize this solution. We start writing the separated product, the sine of x, the exponential of time. This is actually a function handle depending on x, t, n. Also, lambda and b are new function handles depending only on n. For now, we can guess any expression for b. Later, we'll replace b with some real Fourier coefficients. But now, let's take n equal 1. What happens? Well, we get a new function handle depending just on x and t. So this is a surface, and we can visualize it pretty easily. With a simple for loop, we could overlap multiple terms for different values of n. And this is useful just to familiarize a bit with the single terms. Oh, cool. We can rotate, and the alpha function will put some transparency. Now we can copy and paste the code because I'd like to feel the shape of their sum, which is the heat. So we just need to accumulate the contribution from every term to get the final heat structure. And here it is. Now to generalize with n terms, we could insert a slider control to change the number of terms we want to sum. So when you click on the slider, you get the heat surface, and the draw now function will create this nice animation. We can also use a symbolic approach to build the heat structure. Copy the previous function handles, and let's see a trick to convert them into symbolic functions. Just move the argument list from the right to the left of the equal. Now we must define the required symbolic variables and the symbolic functions too. Oh, let me redefine b as a variable, not a function. And let's make assumptions that can simplify to compute the Fourier coefficients later, n to be integer, l and d to be positive. When you run, symbolic output is pretty nice. And just note that symbolic objects can be either independent symbolic variables or symbolic functions depending on other variables. Now to reuse this code, we'd better put it into a local function at the end of the live script. You just type function, you give a name, you define a heat structure as the output. So now we have a quick way to build the symbolic heat structure with the name you like, just by calling this local function anytime you need. Of course, we cannot visualize the symbolic heat object until we fix some values. Now, substituting a symbolic variable with any value, let's say L equal to 5, would be pretty easy. Or click on the sidebar to check quickly. But what if L is already used to store the numerical value? The previous syntax cannot work because we have to redefine L as a symbol. So now we are also able to substitute the symbol L with the numerical L. And we could embed multiple parameters like D and Bn with a single command. But this has remained a function still depending on n. So to fix also n equals 3, for example, we don't need the SOPs operator. Simply place a 3 as a function input, and finally we get the surface, depending just on space and time. And at last we could visualize it. But where is the heat? Actually, the heat is the sum of many of these terms. So to get the heat, we could compute the sum of the first 3 terms, for example, n equal 1, 2, 3. So we can reuse the same code to visualize also the sum, maybe increasing a bit the time duration. And here we are. Cool, we have learned how to embed also numerical parameters into the general heat structure. Now we want to understand the why and where the heat structure comes from. We're going to verify analytical methods to show that not only is the heat structure a solution, but also that it's the solution of the problem. In this small exercise, we verify the heat structure satisfies the heat equation. MATLAB will compute the partial derivatives for us. And when we run, the output shows that the heat structure is indeed a solution. Now, suppose we have defined the heat problem, but we want to look for a solution. The first step will be separation of variables, considering only the boundary conditions. The second step will be Fourier analysis to include also the initial condition. Separation of variables is the idea that solution is product of 2 separated functions, each one depending on a single variable. We substitute this product both in the equation and the boundary conditions, and LiveScript will show the output immediately. We can further separate the equation, putting all the terms depending on time on the left and those depending on space on the right. But the only way for the 2 sides to be equal for any x and t is that they are constant, a negative constant to avoid trivial solutions. So let me write it as negative square lambda. We get 2 separated ODEs, first order for time and second order for space, and that's where exponential and sine show up. We separated the 2 sides here and equated to minus square lambda. Then we solve the ODEs separately using the left boundary condition and suitable constants. Now it's the turn of the right boundary condition. It will force lambda to depend on the rod length. MATLAB can determine lambda spectrum to be any integer multiple of pi over L. So we substitute lambda, we rename all the constant as Bn, and finally taking the product, we have demonstrated that the heat solution must have this structure. But what about Bn? None of these will satisfy the initial condition yet. So any idea about how to choose Bn? At the time 0, the heat structure boils down to a series of sine. But what to do to make it equal to the initial temperature? The coefficients Bn are still 3 degrees of freedom. At the beginning, we recall the Fourier analysis to represent any function as a sum of harmonics. But what is there behind? The magic idea is orthogonality. Very simply, just multiply each member by a sine and take the integral. Now let's compute this integral, which is the inner product of 2 harmonics. The output shows a 0 when indexes are different. So harmonics are orthogonal. Bingo! To satisfy the initial condition, we have this beautiful formula by taking the integral inner product and making a projection along the harmonics. Let's do some more examples. So let's start with a simple function. Let's say phi of x equal x. And repeat the magic Fourier's formula. Come on, phi of x times the harmonic. And then we take the integral from 0 to L. And some factor to normalize. And here are the coefficients in the output. To visualize their behavior a little bit, we can first evaluate some values and convert them to double. So we can create a bar plot and see that they are decreasing with an alternating sign. We could also plot the whole series with the first n harmonics and taking the symbolic sum from 1 to n. So with this for loop, we increment the number of harmonics we are going to sum and then overlap on the original phi to feel how well they can approximate phi closer and closer. We could even add a button to run, repeat the loop, and quickly approximate any other function we are interested in. Now, what happens if the initial condition is a square wave? It has a jump in the middle. Will it work? Yes, more interestingly, Fourier series can approximate even the jump. As a last example, what about a sawtooth? Well, Fourier series performs very well, even in this case, no matter how many jumps you have. Look, amazing, isn't it? Now, we review all the steps together to compute the final solution. First, compute Fourier coefficients of the initial condition. And then define the heat structure by reusing the local function we defined before. The structure satisfies the boundary conditions. Now embed the Fourier coefficients to satisfy the initial condition too. We embed length and diffusivity as well. So finally, to get the heat solution, we take the sum of terms from 1 to n. Of course, we could change the length or any other parameter. For example, we could take an initial condition, jumping from 10 to 40 degrees, and when you run, all computation will be updated. We could also change the material diffusivity, or increase the number of terms. Now, to visualize the final surface, we also fix a time duration. Time decay could be an option. And here is the heat solution. If we change the initial condition, we can see that heat surface is responsive. To create also an animation of the surface, we'd better use a numerical approach where we define a mesh grid and then recompute the numerical heat matrix at each time step. And here we are. Cool. To simulate efficiently, we're going to create a more flexible function to manage all problem input, visualize the solution, or enable animation for a certain time. 30 minutes or 2 hours, depending on material. Going back to the previous section, we copy the 4 steps of solving the problem and scroll down to a new local function, where to paste them in a more compact and reusable way. So here we have a good synthesis of all we have learned to solve the heat equation. Heat solution is part of the output arguments. Remarkably, the function can compute the material diffusivity by reusing the map container built at the beginning and provide a suitable unit correction. It also takes care to convert a given duration into seconds as required. And finally, it can enable animation, checking last input. So testing a function is fundamental. If we run with 2 inputs, we get into troubles. Oops, and why? Actually, we need 4 inputs to compute the heat solution, so we can correct it quickly. And we test again, and now it's okay. So what about 4 inputs? It does work, but coefficients are a bit weird. We'd better add a breakpoint and step into the function. We execute step by step. We continue to next breakpoint until we discover that n was not assumed to be an integer. So we stop debugging and make the correction. Oh, by the way, the oranges notifies that 2 lines are missing the semicolons. Now let's test again with another syntax with graphic. Okay, it works. Let's check a B again. Okay, and let's test the animation. Cool. So now the function is ready for simulation. Our flexible interface can help a lot, but still needs many inputs. Changing values of each of them may be time-consuming, but live controls can speed up this task. We already created such a control at the very beginning to select materials. We use there a drop-down to collect the whole list of materials. Note that when you click on a control, it can run the whole section, but in this case, I do nothing. For example, let's pick iron. There are different types of control, and for the rod length, we could use an edit box to enter a double value. Let's say 1 meter. For the initial condition, we just write the expression, while a slider is perfect to choose the number of Fourier terms. We add another edit box for the duration and a drop-down to select the time units. Now we can also add a button to start the simulation when we are ready. And we see iron has a small diffusivity and reaches equilibrium in about 3 hours. So simulation says to change the timescale from minutes to hours to catch the transient. We can try another initial condition, maybe with a jump, and increase the number of terms. Or pick another material, like a copper, with a larger diffusivity, about 100. So transient dies down much faster in about 30 minutes. So finally, pyrolytic graphite is a very important material in many applications because its diffusivity is greater than 1000 and reaches equilibrium in 3 minutes. Reducing the length, timescale becomes even seconds. So to conclude, we can export now any figure or the whole live script in different formats. For example, we can see the final lecture about the heat equation exported into this PDF file. So I hope you enjoyed, and you can now use the live script to diffuse your ideas. And thanks for watching.